Assalamu alaikum wa rahmatullah. So today we will look once more what we call as the mechanical work done. So if I will just remind you the last expression we found regarding the definition of work done it's notified by this letter W by convention, and we define it as dot product of the force and the displacement. If F is my applied force and this R is my displacement for a given particle, so by this way we define the work done, okay? What about this work done? It's a scalar parameter. We don't care about the direction when we talk about this work done, and we can write this equation likewise by this way as well, because dot product it's a commutative, and by commutative relation we can write down it this way, okay? So if I would just look to this type of relation, basically, if I want to know what's the content in this equation, no matter this is a definition of work done, but if I look to the parameters, this work done involves, it involves number one the force, another fellow that's a particle displacement, but the property of this force we are talking about here specifically, it is constant. It has some constant nature, okay? It is going to act on a system under a constant way, okay? Now if our situation is somehow complicated in a way, if there are some forces which are changing, okay, if the variable forces are going to act on a system, obviously my particle displacements will be different, because when force will act on a particle, it is variable in nature, it has not constant nature. So in a simplest argument, I want to say here my displacement directions will be different, okay? Direction of the displacements will be different under the action of the non-constant force. Means that when my force it is a varying force in nature, okay, it has a variable nature, so the particle displacement directions will be obviously different. So this situation is somehow complicated than this situation which I write here. So it is valid when my force is constant, okay, and the particle displacement is in one direction. Now, I told you as before, if we have the complicated type of situation in a way like when the force acts on a system that has a variable nature, number one, obviously we can guess at the same time, or displacement it will be have the different directions as a consequence of this variable force. So this is a kind of complicated situation, and how we can come across this type of the kind of this intricacy or difficulty, or I can say the kind of complicated situation, there is a one and only one way. So if I will just assume that my particle displacement is going like this, okay, in order to know how exactly we can reach the very important conclusion like here. So at every point, basically particle displacement direction is different, okay? If I want to know the particle displacement here, it will be along this way. If I want to know it here, it will be along this way, okay? If I want to know it here, it will be along this way. So in nutshell, or in principle, when we talk about this kind of curve here, if this is the displacement of the particle, it's a function of time. As time goes on, so as time passes, I have the particle displacement like this. What is basically the beautiful physics content in it? My particle displacement at every instant, it is going to different under the consequence of this force, which has a variable nature. It's not constant in principle. It will change the particle displacement every moment, okay, by one or in another way. So as a result, if I will get the curve like this, I will get the situation like this. This is a kind of, this situation is more logically the complicated one, okay? So it is complicated in a sense the force is variable, the particle displacement direction is everywhere different. So basically when we talk about this kind of definition, it's meant for the constant force, and the displacement is along in some particular direction. Means that displacement possesses here under this definition, displacement possesses a single direction, okay? Displacement of the particle is along a single direction, but under this case the displacements are along the different direction, okay? So how we can come across this kind of complicated situation? There is a only way I can say here. Look, When you talk about this point, at this point, the particle displacement goes along this way, okay? If I will assume that at this point, the force acts on a particle along this direction, okay, it makes an angle of theta with this. Doesn't matter, my parallel component will, once more, it will contribute the displacement, perpendicular component will not contribute here. And that's, I mean, the well-known story as we know from the last discussion. But here, what's my point of interest? Basically, when particle displacement is going to along this way, what it means unto me basically. So my particle displacement, it is indeed a little displacement. This differential displacement I am talking about in principle, it is a little displacement, and my force is in this direction basically. Very important thing here. So for this little displacement, my force looks to be constant, because the force has almost the constant pace for this little displacement, okay? I'm not talking about this displacement as a whole. I am specifically stick to with this kind of little displacement here. So it gives me the kind of this notion or kind of this representation. When we talk about this little displacement for this span of time or for this moment, my force looks to be constant, okay? So if I want to know the work done, obviously work done will be small for this small displacement, but for this bit my force is constant. So this definition is applicable for this small displacement. As I told you before, that the force is constant, so this definition is valid, okay? But specifically, more logically, when I talk about this small displacement, force is going to be constant for this while, okay? So my definition basically holds here for this. So I can write here, obviously when the displacement is small, work done will be small. So small amount of work done, it will be here. I will just represent it by dw, okay? It's meant for the small displacement. For this case, my force seems to be constant, so I have to write here my constant force, but it will have the displacement of dl, okay? Here I use r, I use dl. So by changing the notion of things, it will not change the physics of things, as you know, okay? So here I will just number this equation second, okay? So basically this equation is valid for this bit. As I told you, when we talk about more specifically about this little displacement, my force seems to be constant under the constant force criteria. This definition is valid, okay? So I am eager to write down this definition for this bit as well, okay? See, when I talk about these individual little displacements as for this displacement curve as a whole, so everywhere force will seems to be constant for this little displacement. If I will add up these little displacements, I will get my entire work done, okay? So for that, we basically welcome the calculus. What's calculus? What kind of calculus? Well, more logically talking about here the integral calculus, okay? So if I will just integrate this equation both sides by using the integral operator, okay? So integral differential will cut, I will get the whole amount of work done. It will be as f dot dl, okay? And this is a way which provides us the kind of conclusion how we can come across this kind of integracy. More logically, I can say this kind of compulsity, that this kind of curvature, it has a compulsity because displacement is everywhere different by means of the applied force, which seems to be everywhere different by means of its what we call as the varying nature. So under this way, we come across the very important guy here. So this equation is valid under the case when the displacement is different and force is not going to be constant, okay? But we can make this kind of equation applicable in a way that when we talk about the little displacement element at here and so on, so we will just add up by using the tool of integration. It takes care of everything by this way. So we have the kind of this equation, okay? It's actually the more general form of equation than this, okay? Because this equation it's a conclusion of more complicated stuff here, okay? So if we will do the kind of problem on this kind of equation, okay? So it's a moment to go and discuss the problem for this kind of fellow here. So the kind of this the work done guy I got here, integral f dot dl. My force is going to be constant only for the little displacement element, although in overall pace my force is variable here. So under this kind of complicated situation, we have this kind of equation. It will take care of everything. Okay. So if I will just mention my problem here, for a given particle, if the force is going to act as, if I will just, I have the structure of force like x square y square I unit vector plus x square y square j unit vector. Okay. If the force that acts on a particle of this type that's given this much of newtons, okay, force of this much newtons that acts on a particle. When this force acts on a particle and particle moves in xy plane, when particle moves in xy plane as shown by graph, if the graphics of the particle is also given that, if this is my x-axis here, this is my y-axis, these two mutually perpendicular sets of axis, it forms what we call as xy plane. Okay, if it is given like the particle moves just like this way, okay, if I will just names my A, here it's B, C, D. I will just go for the statement of problem once more. If the force equation is given for a given particle, okay, at the same time our particle it basically moves in an xy plane whose graphics is given, okay, and it's also given from D to C, it is A, okay. By symmetry I can conclude here AB is this A as well, okay, and BC it is also given as, this is also as A, okay. Okay, so if the question basically asks me, if the question basically asks calculate the work done along the path ABC, I need to calculate the work done along the path ABC because this equation is valid here in a sense. Particle displacement is a different, okay, although for particle displacement is in one direction for this linear piece and the particle displacement is different for this linear piece. That's why I just use this equation in a way it will take care of everything, okay. So the problem I have, it's based on this kind of fellow. Look, when we talk about this kind of graphics, what sort of conclusions I can have at the first place? If I will just remind the content from the question here once more, my particle it basically moves in an xy plane under the action of this force, okay. The first part of the problem tells me what will be the work done along the path ABC, and the second part of the problem tells me what will be the work done along the path ADC, and the third part of the problem tells me basically what will be the work done along the path AC. Along the path AC, what will be my work done? Okay, I need to calculate these kind of unknowns here. That's I want to know the work done along the path ABC, ADC, and AC as well. Okay, so first I will just choose to calculate my work done along the path ABC. How we can go and calculate this kind of demand? Have a look here. If I want to know the work done along the path ABC, how I can calculate it? Look, I can just remind my work done here, ABC, okay, it will be integral F. What's F basically? It is x square y square plus x square y square j, okay. Why this I and j, they are just the notions, or we can say the representations of unit vectors along x and y axis respectively. And look, my dl vector, it should consisting with the differential component along the x and the y axis as well, because it is something that's given in a problem. More logically, when we apply the force on a particle, it moves in an xy plane as shown by the graphics, okay. So my differential element, I can write it as my dl element from the given condition, from the given data of question, I can write it as dxi plus dyj, okay. Why so? Because it's given in a problem. When we apply the force on a particle, it moves in a xy plane. My particle moves in an xy plane, so the kind of equation I will get here, For a moment I can write it as dl vector because there is not space of writing this fellow. So here it will be x square y square is I plus x square y square j dot dxi plus dyj. Okay. Look, if I will just simplify this dot product here for a moment, what I will get here is I will get integral x square y square dx plus integral x square y square dy. Hope you are getting it because I dot I, that's 1, j dot j, that's 1, and rest of combinations for I and j unit vectors, when we make the dot of I and j unit vectors, so it always comes out to be 0. I mean to say here, my I dot j is equal to j dot I is equal to 0. Okay. By orthogonal property of the unit vectors and all that, so we got this kind of, I mean, the last equation here. If I will just look to this equation here basically, so I can optimize this equation. This will be the kind of general equation that I can use it for any kind of path here. Okay. So if I will write it here, where I write here right now. Wait for a moment so that I can rub it fully. So here is my WABC that I need to calculate here first, but my work done as introducing the, I mean, the structure of force and the displacement curves, I'm getting here my work done. It will be of this type: x square y square dx plus integral x square y square dy. Okay, look. Specifically, if I want to know work done along ABC, it consisting of the two linear paths. If this picture is visible to you, it consisting of the two piecewise linear paths. The path ABC, I can give some general name to it. It's piecewise linear. Means the piece of this whole path ABC, its AB piece is linear and its BC piece is linear. So I can call this path ABC as a whole, it is nothing but piecewise linear. It's not linear as a whole, but it is piecewise linear. Okay, I hope that you are getting it, what I mean to say. So my work done along the path ABC, it will be yes. See, it will be, I can break this work done into two linear piece paths. A work done along AB plus work done along BC. It is by property of the work done that it's scalar. Okay, I don't need any kind of hectic algebra to deal with scalars rather, because work done along ABC, it will be the contribution of work done along this much and along this much. So either we can write it by this condensed way, or we can write it this way. No issues here. It's one at the same. Okay. I hope that you are getting it, because it's by what we call as by property, that's a scalar property of this work done. As we know the work done, it is a scalar parameter. Okay, we can just break this whole path into the number of two linear paths. I told you as before, when we talk about the path ABC, it's piecewise linear. It is piecewise linear. Path ABC, it's not linear as a whole, but its segments are piecewise linear. Work done along AB plus work done along BC. In aggregation, we will get the work done along ABC. Alright, so here, look, when we talk about the work done along AB, if I will calculate first of all this fellow here, if we WAB, how I can calculate it? Yes, using this. For AB, work done along AB is, yes, for path AB, my x starts from 0 and ends at A, because by symmetry, CD will be by symmetry is equal to BA or AB, one and the same. It will not affect here. Okay, because work done, it's a scalar parameter. Here we are only dealing with the scalars. It's a kind of good news for us. So my AB or BA is equal to CD or DA, one and the same. For path AB, my x is, yes, if I can write it here, for path AB, basically, yes, for path AB, my x is A and my y will be strictly 0, because I am talking about the path along AB that lies on our x-axis. Every point on x-axis, my y coordinate will be always absent. Okay, okay, no issues there are. I hope that you are getting it. So WAB, yes, if I will just use this equation here, yes, my, so dx element, what will happen to this dx? Yes, what will happen to this dx? Yes, if my y is 0 here, I don't care about this dx, so it will be 0. It will be 0 here. So y is here again 0, so this whole will be 0. After solving this integral, I have the y. If I will just integrate it with respect to x, y will be constant, but if I will open the value of y here 0, there is no need to do this, so I will get by this way. The work done along the path AB, it is going to be 0. Okay, now if I look for one more fellow here, the work done along the path BC, yes. So for path BC, yes, for path BC, what will happen? Yes, when we talk about the path BC, whatever the value of x will be here, along this way, the value of x will not change. The x will be my A, okay, comma y. What will be my y? Yes, along the path BC, I'm talking about from this point onwards to upwards. So my x is here, yes. At this point, what are the coordinates of B? X comma 0. Okay, means that my x is here A, and my y is here, yes. My y will be here also. Yes, my y will be also A here. Okay. So along this path, when we talk about my x is not going to change, my x will not change, means that dx will be 0. Dx will be 0, because whatever the value of b along this path, from point B along this path, it will be as if, it will remain same. I hope that you are getting it. It's as simple as, when we start from point B along this vertical path, the value of x is going to be same, A everywhere. There is no change in the value of x. So if I will just look for this integral once more. Now I'm using this integral for the path BC. What will be its value? Yes. Yes. So work done for path BC, yes, it will be, my dx is going to 0 for path BC, yes. My x is A, that will be A square, y square dy, okay. But the value of y changes from 0 to A, because at point B, value of y is 0, at point C, value of y is A. So if I can open this limits of this integral, it will be from 0 to A, okay. So here, if I will just simplify it, it will be A square here, yes. It will be A cube by 3. So it will be, yes, A5 by 3 joules. A5 by 3 joules, okay. And this is basically the work done along the path BC, means it is A to the power 5 by 3 joules. So work done along the path ABC, it will be work done by path, because AB is 0, so I'm getting the work done along the path ABC 0. I don't need to calculate, as it was asked in the question also, work done along the path ADC. There is a kind of symmetry in the problem, so I can say it at the first place without solving this kind of integral, this integral for the path ADC. There is a kind of symmetry in the problem. I can just guess it at the first place. The work done along the path ADC, it will be same as the work done along the path ABC, because there is kind of symmetry. What was absent along this? Y. What will be the absent along this? X. Okay. Either I can solve this integral or this integral, because limits are going to be same. I will get the same answer here. Believe me, I will get the same answer, or if you can do it at your own, it will be the kind of good exercise, and but you will reach this conclusion here. Okay, I am going to skip this part as we can calculate ADC. There is a kind of symmetry in the problem, so symmetry argument permits us here the work done along the path ABC, it will be same along the path ADC. Now, the final calculation here goes to, like, if I want to know the work done along the path AC, how I can calculate this. Very important analysis right now. Look, when we talk about for path AC, basically, if this is A here, this is also A, so definitely if I will draw the diagonal here, this diagonal, it will make an angle of 45 degree here. Okay, it's what I can guess from the geometry of a given graph and all that. Means that if I want to know this tan 45 at every point, if I want to know what are the coordinates here, in general I can say x and y. At this point it will be as perpendicular or base, that will be, or I can say my y by x is tan 45 is 1, which implies my y is equal to x. When I specifically talk about the path AC, my x is come out to be y. Very important. So if I will just make the use of this integral for the path ABC, I will get my work done along the path AC. Yes, my x is here y. So I can put the value of y as x because there exists a differential, because x is here variable, so better way of putting y as x. Okay, so for second integral, yes, I can put x as y, so it will be y square to y square dy. Okay, so it will be here, yes, integral x4 dx plus integral y4 dy. But at this point, see what's the value of x, a, and what's the value of y, a. Okay, so the integral, the limits of the integral is going from 0 to a, and this, the limits of the second integral, sub integral, will also go from 0 to a. Okay, so if I will solve it after giving the limits of this integral and all that, I am getting here a5 by 5 plus a5 by 5. Okay, a5 by 5 and a5 by 5. Okay, right here. Yes, so I will get here at the end a2 times a5 by 5. So the work done I got here along the path AC, it's 2 times a to the power 5 over 5 joules. Okay, so by this way our problem ends, because we got the demands from the question. These are the conclusions that we got. Okay, so this was all about the situation when our particle displacements are different by the application of the variable force and all that. Thank you.